I also put some extra materials on, as you can see there at this website, right? So good afternoon, everyone. This is detection and estimation theory. My name is Professor Pillai. My room is upstairs, so one floor up, 10th floor, 002. You are welcome to stop by there and if you want to talk to me, etc. Right? And some of the faces are familiar to me. So the course has three topics, and I'm assuming that the bare minimum that background you need is probability theory. Okay, something like the 630 here. So let me ask you this. So one thing I would appreciate is I generally don't bring my phone here. So don't. I mean, you can do whatever you want. You're grown-up people, but try not to get distracted with your phone. Phone is your biggest enemy, right? I generally don't bring it up. Today, only reason I brought it, I forgot to bring my watch just to check the time, right? So, as I said, the course has three themes: detection, estimation, and then recently, last year, there, as you probably know, there were courses got revised and so on. So some of the stochastic processes now we also cover here. We can do it in any order, but these items being the core of this course, and I don't want you to get lost in the other details. So we'll do still this way. So more than half about 7-8 lectures will be based on this. Then I will go into the stochastic processes. Okay. So this is detection of signals in noise. And here is estimation of, so generally data comes in, this is R of t. And so our concentration will be here. What do you do with the data and to see whether there is any useful information present? Okay. So let me give you some examples where this is relevant. And before I proceed, you must have, from the output, from the outline I gave you, remember I gave you an outline, and I also have a simple homework because I don't want to scare you in the first lecture, so 2 problems. I think after you listen today, you should be able to do it. We will use this book for few lectures, but so this is the first, the classic textbook, Detection, Estimation and Modulation Theory by Van Trees. It's very nice, it's nicely written. You can start reading chapter 1 and 2. Chapter 2 is where we are going to start with. But he also has some estimation, but then there are better books, and estimation we cover it in much more detail than here. And if you are not familiar with the themes, I'm going to introduce a lot of statistical themes into signal processing. So that's where I think you will see a lot of material which you have not seen, which is what you want to do in a class. Okay. So I also use some of the books that I like in statistics. So this is a book by Rao, R-A-O, on linear statistical inference and its applications. I think I have put it there, right? All right, so let me put 2 more books here. In fact, we will do two theorems by Professor Rao. Again, this is like the Van trees, this is a very classic textbook. So by John Wiley, Linear Statistical Inference and its Applications. The other statistics book I like and I also refer is Rohatgi. I think probability and statistics or something, right? So you can check under Rohatgi. Good thing is nowadays you can buy used copies of these books. So Rohatgi is good for half of it is probability, half of it is statistics. And then in the Papolis book, we also have a good chapter 8 on estimation. So when we come to estimation, a lot of these things I picked up from there and summarized here, but I will also give you some notes on estimation. So generally, this is the problem. The data consists of signal plus noise, right? So that's a general theme. And so you can even write it like this, right? So this is the simplest problem, noisy data. Okay, so the question is now, so this could be, sometimes it could be a constant. That may mean that actually the signal is like this. So the signal could be an unknown constant, right? So that's all the unknown here is. So this could be a constant. Again, it may have three variations because the constant happens to be known or unknown or random, right? Any of these cases could happen. So why would it be known? That's because you transmit a signal and it comes back to you like in radar, right? What happens in radar? You have a transmitter, right? You transmit a pulse, right, of some height. So of course, what you transmit, you know. For example, let's say you transmit this signal. Okay? So this A is known. You know the frequency, though this goes. And if there happens to be a target, then you will get a return, right? So if I call this to be S of t, so remember S of t in this case is a deterministic signal because you know everything about, you know the amplitude, you know the frequency. And when it comes back, of course, you don't know how far this is. You don't even know whether there is a target. That's what. Suppose there is a target, then of course what is going to come back is a delayed version of this. Right? This delay, of course, depends on, this is going to be 2r by c, right? Round trip delay, right? The signal has to go and signal has to come back. So if you call this S of t, by the time it comes back, it is going to be S of t minus t naught, right? But you have no idea, so this is also unknown, right? But anyway, then when this comes, you want to do something. You want to pass it through a processor, and all you need is an yes or no answer. Yes means, yes, there is a target present. No means no target. So we want to do this optimally. Optimum receiver, right? That's what we are looking for. So this is detection. I use the data to make the decision that yes or no. Is there a target or there is? Once you say there is a target, then we can go and try to estimate the parameters and so on. So same thing in communication, right? Even if you are transmitting 1 and zeros in some fashion, right? So this is 1 0 1 1 0. You don't transmit like this, you actually modulate it, right? So you modulate it by some carrier, depending on the transmission scheme, right? If it is PSK, phase shift keying, you to transmit one, let's say you use cos omega naught t a pulse, -1 will be minus cos omega naught t, etc. So this is phase shift keying. Then it goes through the channel, and channel adds noise, etc. Right? Channel may distort the signal. Let's say we have an ideal channel. Channel doesn't do any distortion. But generally the channel, as you know, if the channel has its own impulse response, it could distort. So for example, if this is the signal that's coming in and the channel has a small impulse response, then the output is going to be, this signal gets convolved with this, right? So it will be a little distorted, right? So so if these things are coming one after the other, you see the first pulse extends into the region of the second pulse, causing inter-symbol interference. So it's one type of interference, right? So there are all sorts of problems. So I'm just saying, but in addition to this, we also could have noise, right? So the point is, at the output you see some data. So again, from this data you want to pass it through a receiver, and the job of this receiver is to spit out a sequence. Okay. And if this sequence happens, remember what we transmitted was 1 0 1 1 0, etc. So if this sequence matches with that, there is no error. If this sequence, so you see that there is an error here, otherwise there will be an error. And so you can say that the job of this is to minimize the error. We can start with that condition. So the question is, what is the optimum receiver? So we want to look at these problems in some general fashion, and then in fact we will see that all these solutions that you may be familiar with, actually we can derive it as a result of. So this is the first part. This lecture, next lecture, I am going to, we will study, but we will study it little rigorously. You are welcome to ask me questions anytime. If something needs to be clarified, I can stop and go over again. I also gave you a few other books. Everything is a copy of, more or less a copy of, or topics are arranged the same way as in Vantrease, the book by Poor and also McDonough, right? Some of this earlier I had put it in the library, so you may be there. But I think everyone should own a copy of Vantrease. It's a good book, especially chapter 1. There are 3 volumes, but I think the most useful one is the volume 1 that he has also. Right? All right, so once we design the receiver, remember, sometimes you are going to make mistakes, like here, when a 0 was transmitted, the 5th digit, here we detected it as 1. So that's an error. So that's one type of error. So if you, on the other hand, you can say that 0 stands for no target, and 1 stands for target. So when target is present, we said target is present. So that's good. That's what we should be doing. So you can call that detection. So whereas here, when target is absent, you are saying target is present. So that's one type of error. I'll go over that just to, and here, whereas when target is present, you are saying target is absent. So that's a different kind. Both are errors, but different kinds of errors.
That's a miss, right?
You're right. So since he mentioned this, so you can ask, so in general we may want to compute what is the probability of these things happening. So probability of, so I'll write it. So the receiver detects, I'll give you better notations later. The receiver is detecting the target given that actually where actually it also happens that target happens to be present. So this is probability of detection, right? Actually you are doing the right thing. A target is actually happens to be present in the data, and the receiver is indeed recovering it as one. Then you can, so but whereas receiver is detecting, let's say no target, when target is present. So of course you know how to read this. So I'm writing P A given B, right? So now you can see the usefulness of the conditional probabilities you have learned earlier. So this is a conditional probability. Conditioned on, you are asking for the probability that the receiver detects, says there is no target, given that actually in the data there happens to be a target. So that means you missed it, right? So that will be probability of missing the target. And in a radar situation, you can see that's quite bad, right? Because a bomber is coming towards you and you miss the target. So that means you are exposing yourself to, you are becoming vulnerable, right? So it has big consequences. Similarly, so this is a one type of error. I don't remember whether it is type 1 or type 2. Another one is the other way. You say the receiver detects target. So receiver takes the data, whatever is the algorithm you put in, it processes the data and then makes a decision. The decision is going to be yes or no. Yes means target is present. In a communication scenario, yes means the bit that is coming in is 1. No means, let's say the bit is 0, etc. So whether it's a radar or communication, it's all the same thing. You take some data, process it, make an output. Take the next chunk of data, process it, and put the output. And we want to do this error-free. So this is when no target is present. So when there is no target, if the receiver says target is present, that's a false detection. So this is, in radar at least, this is known as probability of false alarm. So if you think of in a radar situation, what happens is you process some data and then you say, look, there is a target coming, so you start shooting and there is no target. As a result, what you are doing is you are at least exposing your location, making again another, or you are at least wasting ammunition, etc. In any case, it's also a type of error, so we call it type 2 error, I think. One of this is type 1, other one is type 2. I have a feeling I reversed it. So what do you want to do with the errors? Of course, naturally, we want to minimize the errors, right? And so in communication, this is of course very clear to you. That is when there is a bit, when the input data is 1, the output says 0. That's one type of error. Whereas this is the output says 1 when the input is 0. So both, right? So both are, and probability of error is going to be the average of these two in traditional communication. So today we will look into this problem in a little more detail and how do you, so remember the main goal is receiver design. Optimally, everything we want to do the best possible job. Right? Oh, and as we go, then we need to, it's also possible that the signal itself could be a function of time. And so that needs even same problem, a function of time plus noise, that needs some more tools in our at our disposal. So I'm going to wait for that till we do stochastic pro. So you can see where all these things, all the things you have studied here and there, everything coming together. So as I said, it could be and you can go through this also. This is a waveform. And again, you can write the three cases. What are the three cases? The waveform is known, the waveform is unknown, waveform is random. So you may ask, where will you have a random waveform? So listen to this, look at this scenario. Let's say you are under ocean, right? And you have a submarine, right? And submarine, of course, it's being $1 billion. Remember, they spend days and days to maneuver and go through process so that no one knows their location. So at some point, they are going to become. Of course, the first idea is that they don't want to put too much power. They want to be as silent as possible so that no one else is able to, other than themselves and the people who send them, nobody will know after a while their locations. So they have certain secret path and they are supposed to follow that. But the initial few days are you do the maneuvering to avoid detection. Then you see, but nevertheless, for it to move forward or backward, there is a rotor, and you have to. So the rotor is going to generate some noise, and then of course it interacts with the ocean, etc. So these are called the reverberations. So this is not an intelligent signal, right? So it's at the most from a fan and blades, etc., interacting with the water so that there is propulsion to move forward, I think, right? Or sideways or turn, etc. So this waveform, then it, remember, ocean also has, I'm not an ocean expert, but you probably have heard like me, ocean also has various layers of currents and so on, right? Hot water, blah, blah, etc., right? And there is all sorts of, if there is some disturbance somewhere, the waveform goes there. At these various layers, you get reflection and refraction. So there's a lot of mess going around. And, temperature difference creates waves. Wind also contributes to it. Deep ocean, then near to the shore, it's all different phenomena. Sea is a complicated stochastic process. It's unpredictable. But nevertheless, so my point is, even this gets interacts with all that. You can think of this as a time-varying system. So then if there happens to be a ship here, or there happens to be another submarine here, there are trained people listening to see whether they can pick up any signal from here. So that's another detection. So you have a stochastic signal, which is from the turbine of the engine generated weak noise immersed in the ocean. And maybe you put sonar buoys and so on all over, and you get some signals. Then you want to look at these signals and you want to make a decision whether what you are hearing is just ocean noise or is there a signal behind it. But in this case, the signal itself is a stochastic signal, right? It's not an intelligent signal, but the signal may have some structure, like in the wind farm, right? A wind farm, if you can imagine, at least if you transmit something, what is going to come back, you get reflections from all these rotary blades. So it's not an intelligent signal, but there is, if you know how to analyze, you can begin to see that it's not just an ordinary noise either. So that would come under estimation. Once you detect, then of course, then the next question is, what is that signal? What is the source of that signal? All right, so same thing with, so before we go into estimation, the noise itself could be various. So again, if some of you, is there anyone here with any background on stochastic processes, a little bit at least? Anybody without any background? You don't have to be ashamed. I mean, I'm going to cover the material, right? Anyway, all of you are in class, so I'm not going to throw you out. I just want to see. And so stochastic processes, you had some exposure somewhere, or you? Did you do the previous? So he did some of it, right? Anyway, what we need, I will also go over here. So this could be, you see the way I have written everything, not only it is, so this is certainly random. Because the function time is involved, this is a random process. Let me put it that way, right? So we will go over this. So the random process also, there are various kinds of, so there may be processes with some sort of stationary behavior. So if you have, maybe you have heard about weights and stationary processes, etc. Or maybe it's very difficult to see strict and stationary processes, but we can look at this with some structure and no structure, which will be the most general noise will be non-stationary noise. Like in ocean, what happens even if you study the ocean, some region, that doesn't mean you know anything about the ocean, because things change depending on the location, climate conditions, lots of factors. Right? So that will be the nature mostly. But then the noise, at least for stationary processes, you can also, sometimes you can characterize the noise through its power spectrum. Again, saying like this has no meaning, but I will, because we will be, at some point I will go over when we do the stochastic processes, one topic is how to define power spectrum. Because look, after all, it's generating a waveform, so it has some information in the frequency domain. The question is, where are those, where is the most contribution coming in the frequency domain? How do you define, etc. So power spectrum, of course, is a distribution of power versus frequency, and so you could have stochastic processes with power concentrated in this region, in which case we'll call it a low pass, or you might have heard about white noise. That means the power, whichever frequency you look at, there is some contribution. It is sort of flat. So that's one. So power spectrum of the process looks like. Again, if you haven't heard this, what I'm saying now doesn't make much sense. So this is just exposing you to the material that we'll be going through. So again, it depends. If you need to do some work. As I said, this is an advanced course. So we will go over certain things, then you read it, you solve some problems. I have put additional problems at the course website. In fact, the homework number 1 there is a little harder than this. That's why I came up with I made up a easier homework for you this time. And once you get comfortable, you can also, if you want, you can do the other one too. Okay, so you have stationary noise, non-stationary noise. If it is stationary, you can have various power spectrum. As I said, one popular power spectrum is white noise. You might have heard the term. That means, like white light, all the frequency components are present in the noise. So of course, it's unrealistic because look at this. If this is the power spectrum and all the power is present from minus infinity to plus infinity, if you look at the total power, which is the integration of all this, that will blow up. So that's an idealization. It's like a delta function. It's an idealization. So white noise is so in practically what I'm trying to say is, whatever is the frequency region of interest to you, let's say from 2 gigahertz, over that region the noise is flat spectral frequencies. So that you can also call this partially white or colored noise, I think. So noise could be like this, or it could be any general shape also, noise power spectrum. And so we'll study this a bit more when we do the stochastic processes. So in all these situations, and so a little later, maybe in the second half of the course, we will retouch this problem. We'll come back to this problem where it's a waveform plus waveform. And that time you would have heard about, or we would have studied all the various noises. We will know how to proceed this. And remember, and the last case is, not only this is a waveform, this is another stochastic process. So one stochastic process versus another stochastic process. So what is that situation? As I said, this may be the noise being generated by a submarine versus ocean noise. So you want to make that contrast. So both are stochastic processes. So, but nevertheless, one is coming from a target of interest. The other one is, and remember, also you probably have heard like me that that's why half of the detection is done by trained sonar men. They are sonar persons. They listen to it. They have listened to hundreds and hundreds of similar data, enemy submarines, own submarines, what do you call the noise of the whales make. So sometimes the fish also, the big fish also make, yeah, right, things like that. So all this need to be separated. Then you of course process it through the $1 billion computer which they have on board to make additional sense before you take any steps. Because you're not going to transmit the data back to ground. It took them months to maneuver and start hiding, right? So that's detection. Then we go to estimation. So mainly we will concentrate, estimation again, we will concentrate on parameter estimation. So this is so this looks like a simple problem, but here itself, so you have an unknown parameter in noise. So I'm just giving you an outline. Once the outline is over, we'll go into the topic. And on top of this, one thing I forgot to tell you here is you could say the noise is Gaussian, non-Gaussian, etc. So remember, a lot of things going on. Function of time, that's one concept. The frequency characteristics, that's a second concept on the noise. On top of that, this could be Gaussian. This is not Gaussian. Gaussian is a completely different thing. At least you know what a Gaussian random variable is. So we'll define what I mean by, or what we mean by Gaussian for stochastic processes also. Or it could be non-Gaussian, like underwater noise. So the estimation is, we know that the data, like today's temperature, okay, you make some measurements here and there, you know, whatever, there is always error, right? So there is some unknown constant masked by some error. So this is the simplest estimation problem. And then we can, of course, you can pose this as an estimation problem. Estimate this signal. Once you finish the detection, then you can say estimate the signal in it. So this parameter again has two cases that we will consider. This will be random parameters and non-random parameters. So non-random parameter is simply saying that the parameter just happens to be an unknown constant, right? So this theta could be a random parameter or a non-random parameter. So generally the problem is that you make few observations. You have, in this case, I have, let's say, n observations, capital N. Okay. So maybe let me change this over to W. It doesn't matter. W also is for noise. So signal plus noise or a parameter plus noise, so it's corrupted by noise and you have such n observations. So what we are looking for is generally this one. So I'm going to put all the observations as R1, R2, etc., Rn. Okay, so that's a column vector. So I am looking for, so remember the observations are random or observations. These are the observations. So my question to you is, are the observations random or non-random? Anyone? Observations. Random, because look, even if this is not random, this is always random. So random plus something is always random. So observations are random. And what we are finding as the estimator, this is the estimator for theta. Theta is unknown. So this is, look, the estimator of course has to be in terms of what you have observed. What you have observed is data. So this is going to be random or non-random? Anybody? Look at here, this estimator is a function of the data and the data is random. So the estimator also is always random. So it makes sense to talk about the parameter, the properties of a random variable that you studied, mean, variance, etc. So we will do all that in this context because here it is meaningful. In the previous, when we were in probability, we just learned how to characterize the random variables. So of course, look at this, it's already clear to you. If this is the estimator, and if this is the estimator for an unknown parameter, then you know that what do you expect its mean value to be, even without knowing anything. Remember, this is being used to estimate theta, so its mean should turn out to be what? Theta, because theta is what you are looking for. It's only common sense, right? And what will you expect its variance to be, even if you know nothing? Remember, this is an estimator for theta, small, right? So we will see how to use these ideas to design the best estimator. But then that may not make much sense when the parameters themselves are random. So we will deal with both the cases of estimation. So as I said, if the parameter is non-random, that means simply unknown. In other words, the parameter is a constant but unknown. So in that case, if you come up with an estimator, you would say that the estimator should have this property, right? Expected value of the estimator, this is a good property to have. You don't need it, but it is good. So this property is called unbiased estimator. Again, I'll go over all this. The reason I mention this is to see that a lot of things which we have studied earlier beginning to make sense in the, and then you can also look at the variance of that random variable. Remember, data could be R or X sometimes. So this is the variance. Variance, of course, is a non-negative quantity. So as someone said, we want this quantity to be as small as, we want this to be small, etc. So the interesting question is, suppose we are cleverer and cleverer, can you make the variance go to zero? That's a question, because if you're saying, let me drive it down, how far can you drive down? So that's where, so what is your answer? So you will say, look, maybe you put in some more effort, you can reduce the variance, right? Then another person comes in, maybe she can reduce the variance further. So if you have two estimators, of course it is clear, if you have two estimators, and both of them have, let's say, their expected value of theta 1 hat and theta 2 hat, both are equal to theta, then at least you, both are unbiased estimator. So you look at the variance, so there is nothing to pick either between the two. But then if you look at their variances, and let's say you have this property, for example, then which estimator is better? The one with the lower variance, right? But now what is unclear is, how do you know there is, maybe a person might come up with a third estimator, right? Which may be even better than this. Then this will be better. So where do you stop, right? That's a, if this is, then this is the best estimator, if this, etc. So in that context, there is an interesting result which we will study in detail. That's the theorem by Professor Rao, Kramer-Rao bound. You must have heard about it. That says that you cannot, it doesn't matter how clever you are, some of these problems, especially for non-random parameters, the best estimator variance is lower bounded by something. There is a lower bound. So let me symbolically write it like this. So I'll write it as the Kramer-Rao bound. Okay. Remember, it will take us a little bit time to get here, but these are, and this is, you can use it in your research. In other words, if you come up with, so you must have, or you will see, you go through your problem, you plot the Kramer-Rao bound. So generally this is versus SNR. This is the variance of your estimator error. So you use your data, and then so this is your estimator, and then you say this is the Kramer-Rao bound, and you say the other guy did it, his estimator is here, right? So you see, if you have two estimators, this one hugs the Kramer-Rao bound closer. So this is better than this. You have two estimators. This is based on theta 2 hat. Let's say these are based on theta 1 hat, right? So you want to generate figures like this, saying that in fact what it says is, as SNR increases, as the signal to noise ratio increases, the variance is going down. So none of you can be better than the Kramer-Rao bound. That's what we mean by the lower bound. Look at what it says. Any estimator variance is going to be higher than a bound. So this is like the minimum achievable. So if you want to represent another way, Kramer-Rao bound is here for any problem. And your estimator variance may be here. So this may be variance of theta 3 hat, and this may be variance of theta 1 hat, etc. So the best you can do, this is the bottom line, best you can do is you can bring in, you can try to generate so if your variance is here and somebody else's variance is here, and if this is the Kramer-Rao bound, then you know there is scope for improvement. But if you already have an estimator whose variance is equal to this, then you can stop it. That's the best case, right? So again, we will go through all these examples. And so this is parameter estimation, which is the main topic of this course. At least that's the way I rearranged the things. So detection is a small portion for us, as you are going to see, probably with the either two or three lectures we'll finish up. Hello? Hello? I told you not to go over the phone. Keep the phone away. You do this after the class. That's best for everyone, right? I mean, these things are hard. If you don't listen, and if you could do it just by reading the text, it would have been easy. It is not. So your friends can wait. And stochastic processes, depending on the time, there are few things I will definitely do it. As I said, filtering is an important thing, so we will see input-output applications of a stochastic process to a linear system. And power spectrum. And then depending on time, I may also do some Kalman filtering, okay? Then we don't have to, there will be at least two simple exams, one midterm based on the first two topics, detection and estimation, then maybe a small final exam. Then depending on how the class goes, you can, last time we did it, maybe read up a couple of papers and make a small presentation. We don't have to do it, but that way, because that way it's also pushes you, if you're already working on something or you want to look into something, then last time everybody made a 5-minute presentation or 10 minutes, PowerPoint file, etc. You don't have to get scared, you don't want to do it, we don't have to do it. But let's go with the so the simplest problem is something of this form. You have observations 1 through n. Under two hypotheses. So this is called hypothesis testing. So why is it hypothesis? Look at under hypothesis 1, a signal plus noise is present. Under hypothesis 0, you have just noise. Of course, all you have is the data. You don't know we need to use the data to figure out which one is true. So this is, you can, if it is in communication, this is 1 plus noise, 0 bit plus noise. Okay. In radar, it's a target plus noise or no target. So the way I have put you, this is called binary hypothesis testing. But the general problem is Emery hypothesis. Testing. So in general, you can say that there are you have the data set, right? You need to weigh the data set against m possibilities. So these are the Emery hypothesis, H0, H1, etc., m minus 1, and so so what is the question? We need to do the receiver design, right? In other words, you take the data and do some optimal processing to it to determine whether. So today, let me do to explain the concepts. Let me explain everything using the binary hypothesis. Then either next week or week after that, I will also give you the how to generalize this to the, you can, 3 hypothesis is popular, but we can also look at Emery hypothesis. So where is this applicable? Remember, even in communication, you have of course heard about BPSK, right, where it's a 1 bit at a time, or if you take bunches of 2, that's QPSK, right? Because 0, 0 is one hypothesis, 1, 0 is another hypothesis, 0, 1 is hypothesis 2 or 3, and 1, 1 is hypothesis 4. So that's, so you can, that's QPSK, right? So this is QPSK, right? So H0, H1, this is binary or BPSK, right? So this is QPSK, right? Because H0, H1, H2, H3. And you can, or if you take 4 of them, or 3 of them rather, then you go through, what will be? 8, right? Or 4 of them will be 16, right? Yeah. So even 16, so you can use frequency shift keying or phase shift keying or PSK, lots of modulation to transmit. So or PAM, what is it? Pulse amplitude modulation, right? So this you may use a signal like this, the other one may be like, that's pulse amplitude modulation. But by the time it comes out, you may see something like this. So this is what you are going to see. So from here you need to figure out whether, which one is, so this is PAM, right? Pulse amplitude modulation. So this goes here, this goes here. I mean, if it, or you can have FSK, right? Frequency shift keying. You have 4 frequencies. So you modulate accordingly for a short duration, T. This is the pulse duration, right? Same as here. So different transmission schemes. You have maybe in 601, etc. You have already spent time on this. But at the output, everything looks like this. So you want to figure out which hypothesis, which thing is true. Okay. Any questions so far? So another way to conceptualize what we need to do is to say that you have the observation space. That's where you see things. In other words, some R is the data that you have just seen. So what is R is what? As I said, you collect all the observations. Remember, all these observations are about the same signal. So it makes sense to use all, you don't want to operate on each data separately, right? You want to use all the data together. And then what do we do? So one way we could say is that somehow we need to partition this space, say, let's say into 2 regions. So we call this will be so I want to partition somehow the space into 2 regions. So the question is, how do you partition it? So the way I have done, you can see you don't need this, right? So I gave you one partition. That means if the question is, I need to figure out this boundary. So if the signal falls either here or here, we are going to declare the hypothesis H0 is true. Of course, this doesn't mean anything. I just translated the difficulty. I'm saying obviously the obvious, right? Right, this is the decision region or partition region. How do we partition the observation space into either 2 regions or M regions so that, so what do I mean by optimally? When the partition should be such that when hypothesis 1 is true, we want this R to fall in the region. When hypothesis 0 is true, we want the R to fall here. So that's the way we need to do this partition. So remember, look at here. You have a signal, so you have the noise. Noise has some statistics. So it is pretty clear that, look at the R, the statistics of R, or the probability density function. Here we go. Probability density function of course, is this has a probability density function, most likely because of the noise, for sure because of the noise. It's also possible this is random. In fact, next week we'll do some examples of this type. So depending on the hypothesis, it is pretty clear this that the data will have its own distribution. So it's pretty clear to you that you can expect so these are the probability density functions. So they depend on the channel transition probabilities, etc. And right, as I said here, if this is random, if this is Gaussian, Gaussian plus Gaussian is Gaussian with certain parameters. So all these RIs under the hypothesis 1 is Gaussian, and here, with certain parameters. Here it is just because of the noise, so let's say it is also Gaussian with some other parameters. So generally these things will be either known, or you need to figure out from the problem, or sometimes even this may have to be estimated. So estimation within estimation. So we will assume that, because who knows, maybe the model is not there. So you need to use the data itself to do the to figure out these probability density functions. Okay. So in other words, if you plot them, it may have, remember, probability density functions are, so this may be Fr under H naught, and this is Fr under H1. So I am going to assume that we know from the dynamics of the problem, or from the data given, we can figure out all these things. So the problem here is how to partition the observation space optimally. So the question is, what do we mean by optimally? So if you look into the binary hypothesis testing, the truth is and the decision. So truth is, you can have H naught and the decision is H naught. You can have H naught, the decision is H1, and H1, H naught, and H1, H1, right? So this is correct decision, right? And these two are errors. Also, this is, I mean, of course, if it is a bit 0, this is also a correct decision. In radar, when there is no target and you declare as no target, you're not going to be given an award. I mean, that's just a, so that's not much significance. But nevertheless, this is correct decision. So of course, this decision will depend on how do we partition this space optimally. So this is where I'm going to introduce a new idea. So generally in communication, before this you will say, all right, let me take these errors, let me compute the probabilities, let me try to minimize them, etc. Right? Because you can naturally say, look, if you're making error, let's remember, a mantra in probability, I mean in communication is minimize the probability of error, always. So you compute an expression for probability of error, minimize it, go for the receiver. Whereas here we'll take a little more general approach. So all this is known as the Bayes remember, we came across this Bayes earlier, right, in probability. So the same fellow. So here the philosophy is that every action, good action or bad action, has a cost associated with it. Cost Cij, cost is always a non-negative number. So Cij represents cost cost in deciding favor of Hi when Hj is true. And similarly, let me also define, remember, when this happens, there is also a, let me write here. So what is the probability of that? But remember something, truth is H0. H0 is true, and you are deciding in favor of H0. So we don't want to keep writing like this. So the first symbol is going to be, you should always, I'm only going to show the symbols here. So I'm going to write this as this means decide in favor of H0 and H0 is true. Okay, so you can read it out loud. Okay. So this will be decide in favor of H1 and H0 is true. And remember, just a minor stuff, a probability of AB, a probability of A intersection B is the same as probability of A given B multiplied by PB. So you notice that I can write this as probability of H0 given H0 multiplied by P H0, right? So similarly, this is probability of deciding in favor of H1 when H0 is true multiplied by probability of H0. So that's this one. And the next one will be probability of deciding in favor of H0 when H1 is true. So that we can write it as this way, right? Or did I? This one? Yeah. Thank you. You mean this one, right? Yeah. Okay. So how do you read this? Probability of deciding in favor of H0 when H1 is true, right? Just like here, A given B. Given that H1 is true, decide in favor of H0 given that H1 is true, right? Remember, I already wrote it here. The second one stands for what is true, and the first one stands for the decision. And the last one is probability of deciding in favor of H1 and H1 is true. That's the same as decide in favor of H1 when H1 is true multiplied by probability of H1. So let's just make the simple notation that this is P1 and this is P0. All right, so if both the hypotheses are equally likely, this is half-half. This is half, this is half, okay. Any questions so far? I mean, this sounds, of course, you will say, what is the big deal in it? But this is the fundamental philosophy behind Bayes' rule. So that's that anything you do, whether it's a good action or bad action, there is always some cost associated with it. So your receiver design, so we are going to do the optimum receiver design, should be under the principle that to minimize the average cost. So you can also read this as expected cost. So average cost, I am going to denote it as the risk involved. Okay. So the risk is going to be, so remember, there are, so isn't it clear to you? For when you transmit to Pi, here, when you transmit Pi and decide it as Pj, or the other way, right? And so the cost associated with this is, so cost associated with deciding in favor of Hi when Hj is true is Cij. And what is the probability of this happening? That's precisely, its probability is here, right? Its probability is going to be deciding in favor of Hi. Look at here, given that and Hj is true, right? So which is the same as probability of Hi given Hj multiplied by Phj. So this is the cost, this is the probability, we sum up over all the i's and j's, right? To find, that will be the averaging, that's what the expected value. You can write it like this if you want. This is the expected value of Cij, right? So that's going to be a double summation Cij Phi given Hj you can write it in two lines. I already wrote it there for you. So it's Hi intersection Hj. So this is on Ij, this is Cij Phi given Hj multiplied by Phj. So let me specialize to m equal to 2. Remember, this is I equal to 1 through m, j equal to, or 0 through m minus 1, j equal to 0 through m minus 1 in Emery case. So for m equal to 2, this is going to be C00 P right? I just only wrote for, because if it is two terms, what happened? If it is two hypotheses, just 4 terms, okay. So the next question is, I mean, these things are, cost is either given to you or let's say for our case, the costs are given. So remember, this is actually a penalty. This is the cost involved in making a wrong decision in favor of H1 when H0 is true. This is the cost or penalty, you can call it the penalty involved in making the decision in favor of 0 when H1 is true. So this is the decision cost involved in making the right decision. So generally between these two terms, which one will be higher? Or let's say between, which one? Because as in life, right? You pay your taxes, nobody is going to give you a reward. But you make a mistake, then generally the punishment is harsher, right? So you can assume that this is greater than this, and this is greater than this in general. But now look at here, it's an interesting case. Suppose you say, you make the right decision, you are not being awarded. Put this equal to 0, put this equal to 0, put this equal to 1. That means when you make it, then you see, then the risk becomes probability of error, because that's the expression for probability of error. So you can say what you learn in communication is a special case of Bayes. Probability of error is a special case of the risk. Because if you put this equal to 0, this equal to 0, and these two equal to 1, this is type 1 error plus type 2 error. Detecting the bit 1 when 0 is true, or detecting the bit when 1 is true when you detect it in favor of 0. That's the two types of errors. And you want to minimize this is the total probability of error. So this represents the probability of error. If you put CO1 and C10 to be 1 and this to be 0, right? So you can already see that Bayes' rule is a good one. I mean, it's nothing too fancy, because this is actually what we do in communication with this special cause. Now, how do you connect those probabilities that I have given to compute the rest of the terms? So look here. Remember, I also told you that there are two density functions, right? From the problem, we would know these. So we are going to assume this is, so what is the area under any density function? 1, right? So you see the area under any density function is, of course, remember this is multiple integrals, but I'm just not going to complicate. And I hope you are matured enough. These two are not the same functions. So if you really want to be comfortable there, I don't want to start using f and g, etc. But it is pretty clear from the context. Look, this is the density function of these random variables. So there are many random variables, R1, R2, etc., Rn. Same thing here, R1, R2, etc., Rn. But just because I said this is under the hypothesis H1, this is under the hypothesis H0, even if I don't put this subscript, it should be clear to you that these two are two different functions, right? But just in the beginning I'll put, but most likely I won't be putting this 1 and 0s, okay? So if you integrate over this whole space, remember, over the entire observation space, what do you get on each one of them? Anybody? 1, that's what we said, right? So, but you see, what we want to do is, we want to find out how to partition this whole space into two regions. So what we want is, we want to partition the whole space as the disjoint union of Z0 and Z1, right? Z0 union Z1, and Z0 intersection C1 should be what? Null, empty set, right? So how do we do this? So you see, so if I replace this S by so if I can replace this by Z0 union Z1, same thing here. So you get two identities, right? Remember, they being disjoint, you also get F arg1 H1 dr plus C1 F arg1. This is trivial. This is true for any density function. But this will help us to, same thing here, F arg1 H0 under n plus Z1. So of course, if you want this term, that's 1 minus this, etc., right? So anyone, Now you should be begin to see how to compute those 4 terms. So what is this probability? Look at here. So what does this mean? This means if you take, for example, let's look at this term. This says, of course, the hypothesis 1 is true, and we are integrating over Z naught. R is being integrated over Z naught. That means the R falls within Z naught. That means if R falls within Z naught, we are going to decide it as H0. So this is actually the probability of deciding in favor of H0 when H1 is true, right? So this one, so now we can, remember that's how so this is, of course, probability of deciding in favor of H0 when H1 is true. And look at here. This is you are deciding in what is the probability that R will fall in Z1. If R falls in within Z1, we are going to declare it as H1. So this is the probability of declaring in favor of H1 when H1 happens to be true. What is truth is here, right? So similarly here, because what is the probability of R falling in Z0? If R falls on Z0, you are going to declare it as H0. But H0 happens to be true. So this is the probability of deciding in favor of H0 when H0 is true. And here, this is the probability of deciding in favor of H1 when H0 is true. So you also have these identities, okay? Right? This of course makes sense. Look here. If H1 is true, look here, trivially, if H1 is true, either you have to decide it as H0 or you have to decide it as H1. So if it is not one, it's the other one. So that probabilities are equal, right? Right? So let me complete this, then we'll take a short break and then I'll do a problem. I think that's all the time we will have for today. But that will also give you enough material to do the 2 homework problems. So you see now what I'm going to do is I'm going to plug in for all the expressions. So this is the Bayes procedure. So R is C naught not P naught. Deciding in favor of H0 when H0 is true, plus deciding in favor of H1 when H0 is true. So what is it? F or H1, right? So either way, you can just inspect it and write it or write it from there. All right? Now what do we do? It's a mess. You have Z0, Z1, etc. So we can do it 2 different ways. I'm going to bring everything in terms of Z0. You can redo it in terms of Z1. Look here. It's easy because anything in terms of Z1, I can rewrite it in terms of Z0, right? So I could have done it without this step. So what I'm trying to say is I'm going to write this whole integral as 1 minus integral over Z0 F R given H0, right? And similarly, this is 1 minus integral over z naught f r given h1 dr. Same integral, but over the complement region. Okay. So let me put it together and let me see whether I can write it here. So you have a constant C. Look at here, there is a constant. So C10 P naught plus C11 P1, right? P1 plus an integral on Z naught. So let's collect all the terms. Yeah, hold on, let me see. Hmm?
Fact C10, maybe should be C00, and this is the right part.
You talking about here?
Another,
Here?
no,
Yeah.
the,
Inside the integral or? Tell me again, this is correct, right?
yeah, that's correct.
Right, so this is C10 P naught. When you, remember, this is being multiplied by this one, isn't it?
Yeah,
So that's what I wrote, C10 P naught.
yeah.
All right, so what are you saying now?
Oh, please go on.
Yeah, hold on, let me see. Something is not right. You know, everything is good. So, let me see which way it so I took these two, right? I took C11 P1 is here. So you see this is higher than this. So I wrote it in terms of CO. So we know this is positive, right? And this is definitely positive. Minus, and P1 is here, P1 is here. So everything is good. And the other one I'm going to write it because C10 is hitting but the minus. So I'm going to pull the minus out, C10 minus, because this is plus, so that's going to be C00 P0 FR given H naught dr, right? Right? Okay, everything is good. So you see this is positive, right? Because that's the reason I put, otherwise this is positive because cost of making a bad decision is always higher than cost of the reward for a good decision. Probability density function is positive, these probabilities are positive. So positive minus a positive, right? So what can happen? Remember, punchline is coming, so don't lose, don't stop paying attention. Pay attention here. So look here, this term and this term, which term will be higher? Anyone? You need to think now. Remember, this is even more general than minimization of probability of error. Probability of error I showed you is a special case of this. You have two positive terms. Which term is higher? Or let me ask differently. Can you say, is there a reason to assume what can happen? Is it always this term is higher than this or the other way, or anything could happen? Look at here, hello, everyone, look here, which term, I see two positive terms, something minus something, everything is within the integrand. So what can happen? Two cases can happen. What are the two cases? Remember, it's a positive term minus a positive term. What can happen? X minus y. X and y are positive. Yes?
It can stay positive.
Or? Right. That's true, right? Because even if x is positive and y is positive, there are two cases. X minus y is positive or x minus y is negative, right? Look at here. Only consider this case, of course, x is positive, y is positive. Anything here, x is greater than y, right? So if it is x minus y is positive here, but x minus y is negative here, right? So my point is, look at here. You take somewhere here. You fix r. Listen to the argument now. You fix r. So the r is given. Once r is given, this number is known. This number is known. Remember, these are two different numbers because two different density functions. All these numbers are positive. So you have a positive number minus positive number. It's pretty clear to you that depending on the data, this is the only place you have variation. Depending on the data, this could be larger or this could be larger. So we have two cases. Everything depends on the data. The data needs to come in, I need to plug it in. Then if this number is larger than this, and if you collect all those terms, this whole integral is going to be positive, right? Whereas if this number is less than this, you collect all those terms are going to be negative. So it is pretty clear. Look, your goal is to not to maximize but minimize this condition. There is nothing to minimize here. Again, punchline is coming here. There is nothing to minimize here. This is constant. So your freedom is here. Question is, should I put this r in z0 or should I put this r in z1? You put it in such a way so that this quantity turns out to be negative, so that from something is subtracted and you do the minimization, right? So the argument is, so let me write the two cases here. So you have two cases, CO1 minus C11 multiplied by P1 Fr given H1, and the, let me just write a little smaller. So CO1 minus C11. I'm just copying what we have there. And we need to compare this point by point, at least conceptually, these two quantities. Remember, the key is here R. Where does R go? So you see, as I said, if this, so let's do the obvious case. If this happens to be less than this, then this will turn out to be negative. And then indeed, you should keep that R in Z0 because that's the right place, because then something is being subtracted from a positive quantity and you are helping to minimize this. So if this quantity is smaller than this, we should decide in favor of, decide the R in favor of Z0. That's what I mean by H0. And conversely, if this quantity is greater than here, don't put it in Z0 because you are only going to increase the risk. So if it is greater, you should decide in favor of H1. And this is the Bayes decision rule. This is the punchline, right? So try to understand this. So remember, everything, data is the king. Once you get the data, you plug in all these density functions and see, so there is only two possibilities. The left side is greater than the right side, in which case this quantity is positive and this is not the place to put it in. Then of course it should be the other place, which will be Z1. On the other hand, if this quantity, if R is such that this quantity is negative, that's the right place to be here. This R should be in Z0. You can also rewrite this, you go home and rewrite this in terms of Z1. The terms, you'll get exactly the same result using the other argument. Okay. You don't seem to be convinced, or you understood? Yeah, okay. So you decide, we are not going to write decide, we will just write it like this. So this is called, so this is like a threshold detection. Let me bring in all the data terms to the left side. So I keep saying, remember, it's all minimization of the risk leads to so I put all the data terms on one side and I take all the other terms on the right side, you see. So look at here, data is only coming in here and coming in here. So I brought this, and there is no problem in bringing in. The density functions are non-negative, so I can divide by that. This quantity, remember, we already said this is positive, so I can divide it by this way also. So this is C10 minus C00 multiplied by P naught divided by C01 minus C11 multiplied by P0. So this quantity, generally the symbol used is capital lambda R, and this is known as the likelihood function. You are going to hear this word likelihood function, likelihood again and again, but this is the likelihood function. So you see, you have the receiver in front of you. You do something to the data and you make a decision. So the decision is what we went through all this. So your data comes in, you form the lambda R, and then you compare it with the threshold. If this lambda R is greater than the threshold, you decide in favor of H1. Otherwise, you decide in favor of H0. So I'm going to do a few examples, and in fact, I'll do one example. That's all. Probably we'll have the time. But you see, nothing is common sense. It's not like saying you just do FFT or something, right? And it is complicated because you need to figure out how to get this density function. So there is some work involved. Okay. And look at here, this is a non-negative function. So you can also take, sometimes if it is easier, you can also take logarithm on both sides. This is non-negative. I don't see anything negative here, the non-negative. So we can also say that logarithm of lambda R is greater than or remember, log is a function, log goes like this, right? So this is logarithm of eta. So this is called log likelihood function. So to summarize, we haven't, the concept is very simple. You have data and it obeys certain probabilities. So you're going to take action. Every action has a cost. Cost multiplied by the probability will be the likelihood of that involving that cost. You find the risk is average cost, and you minimize the average cost. That led to the likelihood function is the optimum solution. So there is no better test. Nobody is going, if you use the minimization of the risk as the criterion, you like it, then this is the best you can do. This is the optimum receiver. Now, of course, all the attention need to be paid how to solve a problem, details, how to work it out. But so you might keep hearing optimum receiver is the likelihood function. So we have one more hour if you want. Let's take a few minutes break and then we'll go. Here is a homework. So don't take too much time. And I'm going to do a similar problem now. So what I expect you is you do it and submit it next week. I'll give you the solutions, etc. So 2-3 minutes, that's all. Okay. Okay, we can, I guess everybody is here, right? So I guess, I hope you got the punchline, right? You compute this. As I said, you go home and try to redo this just as an exercise. It's not a big deal, right? You can express in terms of Z1. So look, if this whole term is negative, then this R indeed belongs to Z0. That's all I said. If this is negative, R belongs to Z0. If it is positive, don't put R in Z0. There is only one place to put it in. You put it in Z1, right? So that's what is written. So if this term is less than this term, you decide in favor of H0. If it is greater, you say that the R which the data represents target. All right. So I did the same thing here, and sometimes you take the likelihood function. I mean, you take the logarithm. So this is known as, the abbreviation is LRT, stands for likelihood ratio test. LRT is the optimum. So to summarize, the Bayes procedure is to minimize the risk, and that leads to optimum receiver as LRT, right? Then now it makes sense. You can read what it says, right? The Bayes procedure is to associate, you need to go through all this. Every action you associate a cost. That happens with a certain probability. So you add up all the cost averaged by the probabilities. That's the average cost or the risk. Then you compute the expression. You want to put R in such that the risk is minimized. So if this is your whole space, you put R. If this, remember, this quantity, if it exceeds the threshold, then you say this point belongs to Z1. Similarly, you have to go through all this. So at the end, you will be able to do a partition saying that this is Z1, this is Z0, this is Z1, this is Z1, the rest is Z0, etc. You have to go through this at least conceptually. Then you will do the partition optimally, which is another way to write this is you go through, as soon as you get the data, you compute and either compare it with a threshold, or you take the logarithm of the likelihood function and compare it with not with the eta, with the log eta, a new threshold. Sometimes you can call it gamma. So that's the log likelihood ratio test. As you are going to see, sometimes the second one is faster. Now, so as I said, please go home, and maybe a good thing to do is rewrite this in terms of Z1. These terms are going to flip. This will be slightly different. Again, you go through this exactly the same argument. Okay. Now, sometimes when you, we'll discuss this in detail. I want to do an example so that you know how to do this. Sometimes, ultimately, remember, you look at the left side. You keep manipulating, it will turn out to be a function of the data. That's all you have. So you don't want anything else on the right side. So, so the likelihood function in its simplest form, it doesn't make much sense to you, but I'll say it anyway, is also known as the sufficient statistics. And we will see what is the. So that's the simplest form of once you manipulate the likelihood function, whatever is the simplest form of the data, you call it the sufficient statistics. So your sufficient statistics, I mean, if you manipulate, you may get a different threshold here, different constant, because there may be some constants here. You bring all those constants to the right side, you get a new threshold, etc. So bottom line is a sufficient statistics is compared with the threshold, right? So we will need to compute all these things, PD, PF, PM, etc., right? So what is PD? Probability of deciding in favor of H1 when H1 is true. Probability of deciding in favor of H1 when H0 is true. PM is missing. That is probability of deciding in favor of H0 when H1 is true. Right? and at least we have these expressions. So you will decide it in favor of, so you have R given H1, and you integrate over all Z1, you get that one. So you can write it like that, which I have it there also. So here you have the data given H0, you want that density function, but you integrate over Z1, that gives you probability of false alarm, right? It makes sense here, right? Look at here. So if this is your two regions, I'll make it simple. See, R given, it could be H1 or R could be, either one could be true, right? R could be H, so it could, data could fall here. It also, if it falls here, you are going to decide it as Z1. But it depends on the source. If the source is under H1, then this is fine. That's a probability of detection. But if the data falls here, that's bad, because then you are going to decide in favor of H1 when H0 is true. That will be false alarm, right? Same thing here. If that data falls here, once it falls here, we are going to declare in terms of Z0, because we have already done the partition somehow. Then if it is H1 is true and you decide in favor of H0, then that's probability of miss, right? So you see physically, right? So we will, in each problem, we will also need to compute all those things. And so what else? As I said, sufficient, maybe it's a bit too early, but nevertheless, let me mention. On the other hand, now if you simplify the problem, you can also see it this way. I mean, it doesn't have to be Gaussian or anything. So picture, you have L. L is your sufficient statistic. You are comparing L with some eta. Remember, this eta need not be what you started with. L is, of course, a function of R. You simplified everything, right? So L is a random variable because the data is a random variable. So the data, depending on which hypothesis is true, it will have its own density functions, right? And so you can physically see your eta is here. You have two density functions and you have four regions, right? So anyone, what is this probability? What is this probability? Anyone can physically see? So for example, look at this red piece. This is the probability of, right, so that's the, integrating the density function of L given H0 from eta to infinity. Why will you do that? That means L exceeds the threshold. If L exceeds the threshold, you are detecting in favor of H1 when H0 is true. And what did you say? Right, that's the probability of false alarm. So physically, you should be able to, physically you can see that this area, this tail represents the problem. So if this density function has a fat tail, then probability of detection is high. Now how about this region, which I have written like this? Anybody? So again, let's see what it is. So this is the integral from minus infinity to, you are integrating up to here, eta of this density function of FL under H1 dl, right? That means L is less than, L is less than eta. If L is, right, I'm only integrating up to here. That means L is less than eta. If L is less than eta and H1 is true, that's the probability of that means you are deciding in favor of H0 when H1 happens to be true. So that will be deciding in favor of H0 when so if you want, you can also write this as in terms of L now, right? So you have a lot of options now, right? But this will be minus infinity to eta, right? So this will be probability of miss, you are right. And you can copy this expression here. So this is also eta to infinity f of L under H naught dl. Okay. And this will be eta to infinity f of L under H1 dl. Okay. So we will use these expressions. So I think I am done with the theory for today. So let me show you how this all comes up in. One thing you cannot do is you cannot read the theory and walk away. You have to, so to test whether you understand this is the best thing is solve a problem. So I do a problem, then you do two at home. That way you get familiar with it, right? So let me get rid of all this and I'll keep the minimum things there. Anybody, any questions before I go into the problems? I'll do a couple of problems. If I can finish it, we'll do it next time, the second one or third one. How much time we have now? So remember, I gave you this problem. Now we will do this. Anybody knows what is IID? The noise samples. So remember, this is obviously I am sampling the data. There is an unknown plus noise or just noise. We don't know which one is true. That's what we are trying to figure out. The IID means independent. The noise is independent. Noise samples are at least independent. Identically distributed. What does that mean? That means if you know one noise sample is Gaussian, all of them are Gaussian. It's all coming from the same family. And if one sample has variance sigma squared, all of them have sigma squared. But they're all independent. They don't have to be, but we'll start with the simple problem. So I will keep using this term IID, okay? That means all the, to be clear, the joint density function of the noise is what? Anybody? What do I mean by independent? Hello?
The multiplication of each one.
Right, so it's the product of all the marginal density functions. Again, this is a crazy notation. I'm hoping you understand. This f and this f are not the same. So this is fi's, right? The density function of each one of them, whereas this is the joint density function. So again, we are all mature enough, you understand. But identical will mean that all these density functions are the same shape, same exactly. They are independent, but they are. So this, this could be f naught, then all of them are f naught. Otherwise what? One sample could be Gaussian, the second sample could be Poisson, etc. At least that's not the case. Everything is from Gaussian. Moreover, when I say identical, I also mean their parameters are the same. So if it is Gaussian and it has two parameters, mean and variance. So I'm going to assume that, in this case, I'm going to assume all the noise variances are Gaussian with the zero mean and variance sigma squared. If I put an I here, then they are not identical. If I put an I here, they won't be identical because they have different variances. But because I am saying identical, so that problem we'll do some other, you can do it at home or we can do it next week here. Or if I have time, we'll do it now, afterwards. So let's I'm going to assume, so you can see already problems inside problem. So this is the assumption. All the noise is zero mean, and this signal is, this is a deterministic. That means it is unknown constant. Okay. Again, I am not trying to estimate anything here. I just want to know which one is true from the data. Either the first hypothesis is true or the second hypothesis is true. So remember, as you can see, I need to find out these two density functions. So look here, we will do, when this is also Gaussian probably next week. So right now we could say, why not this be another Gaussian random variable with perhaps some mean and some other variance. That will be a little more complicated, so we'll wait on that. A constant plus Gaussian is what? Anyone? Gaussian. So what is if the hypothesis H1 is true, then you have to look at this line. What is the mean of this random variable when it is here? A, and variance? Huh? Oh, again, remember, remember that would be true if A is a random variable. A is a constant. Right? So remember, the variance of R would be under H1 would be expected value of the random variable minus its mean. What is the mean? Mean, A, right? So mean squared. Ri minus A, look at there, is W squared. So the variance will be only of Wi squared. But that's given to be sigma squared here. And so this would be, so everybody knows this, right? A constant, Gaussian plus Gaussian is Gaussian, constant plus Gaussian is Gaussian. This is Gaussian. So I can say that this is normal with mean A and variance sigma squared. This is of course normal with this mean 0, variance sigma squared, right? Because that's the data given. So this is under H1, this is under H0. This is where you need, if you need to brush up, you need to brush up. Okay, so if you begin to make mistakes at the first step, then you're not going to get the right answer. Okay. You may understand all the theory, and this is where you need to solve the problems. You need to see how problems are solved. So we need FR under H1. Remember, R is R1, R2, etc., Rn under H1. And we also need FR under H0. So this is R1, R2, etc., Rn under H0. Now, the second one is easy because because this is the same as FW1, W2, etc., Wn. You can just look at the data, right? Under H1, look at here, under H0 it is just Wi's. And all the Wi's are given to be independent. Look, it is step by step. So of course here you can say it is FW1 multiplied by FW2, etc., Fwn. And each of this is of this form, right? Square root of 1 over 2 pi sigma squared e raised to minus ri squared, right, over 2, because this is the same as under this one R1, R2, Rn. Under hypothesis, I'm only looking under hypothesis H1, right? So this of course is 1 over 2 pi sigma squared to the power n by 2 e raised to minus ri squared over 2 sigma squared, right? So we need to take the ratio of this. So we need to take the ratio, but I haven't found these quantities here. So we found the denominator. Okay. So how about the numerator? How will you go? Look at here. Here to here, it was easy. And so because W's are independent, that is true. Now what happens if you remember W1 and W2 are independent. If you add a constant to them, you get, let me call that X1 and X2. My question to you is, are X1 and X2 independent? Well, the answer is right. I hope you can prove it, but the answer is right. Once you are confident, then you know that under H1 also the data is independent. So I can write here, this is also, either you can write A1 H1 or this is true. But look at here now. Suppose this is Gaussian also. Then what? So this is, let me call this to be X plus W1, X plus W2. I'm going to call them Y1 and Y2. So this is the problem. R1 is X plus W1. This is X plus W2, R2. W1 and W2 are independent. X is Gaussian, W1 is Gaussian. So this is Gaussian, this is Gaussian. My question is, are R1 and R2 dependent or independent? Huh?
Guess.
You guess what? Anyone? A little more strongly? Dependent or independent? Remember, you don't have to, first of all, you can try to find the correlation. You will see that they are correlated and certainly dependent. So that's a messier problem. So this is, it's always, not always true that everything is independent, but in this case they are independent. But each of them is, remember, each of them will have of this form. The variance is 1 over 2 pi sigma squared because it's given here. Here, variance is this, and they have a mean AI. So this is e raised to minus Ri minus a the whole squared over 2 sigma squared. So which is what I'm going to put it here, right? So this is the product of 1 over square root of 2 pi sigma squared e raised to minus Ri minus a the whole squared over 2 sigma squared, I equal to 1 through n. So again, you will get this one, 2 sigma squared to the power n by 2. All the product becomes summation Ri minus a the whole squared over 2 sigma squared, I equal to 1 through n. In this case, you are lucky because this, anyway, lucky or no, it's the constants cancel. And this needs to be compared with the threshold, right? So look at here. The numerator, of course, in this case, if you expand, you get e raised to minus 1 over 2 sigma squared. Then you have summation Ri squared minus 2 a sigma Ri, right? Then you have summation a squared, right, over e to the power minus half 2 sigma squared summation Ri squared, right? You see, this term cancels with this, right? This is exactly, the first term is exactly the same. So we end up with e raised to minus 1 over 2 sigma squared. So let me take the 2 sigma squared inside. You have a over sigma squared, sigma a Ri, I equal to 1 through n, right? And what is this? Anyone? When you expand this, what do you get? Na squared, right? So that's Na squared over 2 sigma squared, right? With a minus sign, right? You see, now you can see why the log likelihood is better, because exponential is sitting there. So if you take logarithm on both the sides, we get rid of the nonlinearity. Okay. So this, of course, you can, let me take the logarithm on both the sides. So you get something less than or equal to log eta, right? And this side you get a over sigma squared summation Ri I equal to 1 through n minus n a squared over 2 sigma squared. So let me see, this is what this is not still sufficient because I see constant. Let me take this constant onto the right side. So this, of course, I can write it as, and I divide by, because this is, what is this? You are familiar with this. You have a set of observations, you are taking average. So I add up all this, so I divide by n, but I just divide by a constant. So you understand, right? Taking this constant, you don't have to worry. You are just adding or subtracting. That's only when you divide by, you have to worry. So first I am going to take logarithm of eta. I'm going to add n a squared over sigma squared, right? 2 sigma squared plus log eta. Then I must have multiplied by sigma squared over a, right? Right? So sigma squared over a. So the right side becomes now a cancels, and you're not paying attention. Also and also an n, right? So n cancels, a cancels, sigma squared cancels. So you get a by 2 plus sigma squared in a, right? Log eta. Oh, so if you want, you can call this gamma, okay, a new threshold, right? It's a constant. Look at the right side. Everything is a constant. I look at the left side. So we brought it up to this. So everything comes like this. So the test now reads 1 over n sigma. 1 over n is not necessary. I hope I did this right. Okay. So this is the optimum test. Look at here. This is the simplest form. This is what I was talking about earlier. This is the simplest form of the data. So this must be your sufficient statistics in this case. So naturally you can find this out. So I need everybody in the class. So don't go and get out of the class, because we need a good class. And the things get, especially the estimation gets to be more interesting, and you learn things which you have not seen elsewhere. That's why the course is useful. So stay with me, but you do need to do the work. You can't just come back and listen to me alone, right? So once you get, this homework is very easy. Once you get comfortable with this, if you have tried to do the homework, which is also on the web, and then at least to those of you who have done it, I can give you the solutions also. But this is not over. The problem is we only have done half the part. We just found the receiver. So what will you do? So saying this is now makes sense. You are saying, look, if you have noisy observations, so long as here is a theorem. If you have noisy observations, so long as the noise is Gaussian white noise, the best thing to do is take the average and compare it with the threshold. And if it exceeds the threshold, you say the signal is present. If it goes down the threshold, what is eta? I unfortunately removed it. Can someone read it to me? Eta was what? C01 or C10? C10 minus C00 multiplied by P naught, right? And CO1 minus C11 multiplied by P1. Look, if you take the communication theory approach, these two quantities are 0 because this is the cost involved in making the right decision, 0. Cost involved in making the wrong decision, you take it to be 1. So this factor is 1. Take the hypothesis to be equally likely, then this term is 1. The logarithm of 1 is 0. So in that special case, you see the threshold comes out to be again meaningful, a by 2. So that means if you look at the signal, if it is above a by 2, you declare in favor of 1, or the signal is present if it is. But if the cost is something else, then the threshold will be going up or down. Okay. So this is the biggest criticism against this method. So someone could ask, how do you decide this cost? See, I just decided that these are zeros and these are ones. That's just a common sense. Now you may decide this is 2 and this is 0.5, etc. Then you will get the threshold will be different. That means the threshold is subjective. Human interaction is coming up. It's not that that is bad, but how to even get away from the subjective decision will be probably the topic of the next week after I do 1 or 2 more examples. At least let me finish this example. As I said, it's not over. Any questions so far? No, we have time, so let's try. So I need to find out probability of detection, probability of false alarm, things like that. What is it now? Yeah, what is the question? Huh? The R, look at here. If it is under hypothesis, I can either write W or I can write R, right? W is the same as the observation. If it is, if you know it is H1, then you have to write you have to write Ri as A plus Wi. So if you don't like it here, of course I can write it as W1. It's one and the same thing, right? Remember the denominator, look at here, it's under hypothesis H0. The numerator, that's why I kept it as R1. Otherwise I have to, if you want to replace this R1, I have to write here A plus W1, right?
So they are independent, right?
Which one? Look here, because A is a constant, A plus W1 is independent of A plus W2.
Yeah.
Right, that's why we were able to write like this. So just because I do this in this problem, it doesn't mean in all the problems things are independent. You have to do each problem. That's where you need to do it, and you make some mistakes and you correct it. So you just need to work a lot of things at home, right? So you are a champion of probability. So excellent applications of probability. Now you begin to see why what we did there makes independence, etc., etc. Now again, if you need to brush up, you need to brush up on probability. So we just found the best detector. Best detector is form the average, compare it with the threshold. The next question is, what is the probability of detection? What is the probability of false alarm, etc. in this problem? So let's try to compute them. So somewhere we had the expression which is gone. For example, we'll start with the probability of detection. Probability of detection is what? Remember, a couple of expressions, right? Detecting in favor of H1 when H1 is true. This is, you can write this as, I also gave you this, right? L under H1. And the integral goes from where to where? Remember, you have L with some density function, Fl under H1, we need to find out. Then you have the threshold gamma. So this is the probability of detection, right? So that's gamma to infinity. Look here, I am not making this up. Look here, if L under H1, if L exceeds gamma, it's always H1. But if it happens to be under H1, then it is probability of detection. If L is less than gamma, then you are going to decide it as H0. So probability of false alarm is also deciding in favor of H1 when H0 is true. So that's gamma. When H0 is true, if L exceeds, remember I write this fast, I hope you understand, I'm just going along, but it is, everything is physical, right? So you see, these are the challenges from probability. How do you compute this? Nobody is going to give you all this. You need to use the problem at hand. That's where it's a very nice combination of what you have learned earlier, if you learned it. So let me get rid of all this stuff so that, remember we have L here. So you need to do like this in each problem, at least the 2 problems there, and I think there are 2-3 more problems on the website homework, which is what that's a little harder than this, but once you do this, you can do that too, right? So remember, R is of the form, each Ri is A plus Wi or Wi under H1 and H0, and L is given to be, we decided, we figured out L to be this, right? So what will be, what will be the L under the 2 hypotheses? So look what L is, you're adding everything. So if you add A n times and divide by n, what do you get? So you get A plus some W bar and here W bar, right? Under H1 and H0. What is W bar? W bar is W1 plus Wn over, again probability. What is the mean and, so you see, if you add a bunch of Gaussian independent random variables, what do you get? Gaussian. So next question is, if you can do it right, what is the mean and variance of that Gaussian random variable? Anybody? What is the variance of this random variable? Anyone? All the random variables are independent, so what happens to the variance? Again, you need to brush up this. Variance actually adds up, so that's correct. But if you divide by you can divide by different constants. If you divide by a constant, what happens? Remember, variance is the square of something. So the constant also squares, but the numerator, variance still adds up, divided. So n sigma squared over n squared, so it's sigma squared over n, right? So this is normal with mean zeros, variance sigma squared over n. And this is also normal because a constant plus the same Gaussian random variable. This is a constant, so the variance doesn't change, only the mean changes. So this is A sigma squared over n. Okay. So if you draw this, pictures are always good. Look, this is the origin. So one density function is centered around the origin, right? Which density function is that? Look at here, with the mean 0, so that's FL under H0. The other one has mean A, so that if A is somewhere here, then the other one is like this, right? So let me use a different color. So that's like this, right? So this is FL under H1, and that is peaked as at A. And where is the threshold? Anybody? Huh? A by 2 plus something. You look at there, right? So threshold is somewhere here, between here and here. Look at here, A by 2 plus something. Of course, if eta is 0, if you have the communication assumption or both the hypotheses are equally likely and the cost is either 1 or 0, eta would be 1. So this term goes away, you get the threshold to be A by 2. But if this is not 1, then you have a bias, okay? So eta is, let's say, somewhere here. And then this is PD, right? This is, right? And where is PF?
Under the background.
Remember, you look at the thing. So PF is going to be like this. So what happens? Look at here. One phenomenon. What happens if I move the threshold to the left? What will happen to PD? Increase or decrease? Huh?
Increase.
How about PF?
Increase.
Suppose I move it this way. Both will decrease. So that's a phenomenon we'll prove. PF and PD, unfortunately, you want actually PD to increase and PF to decrease. But if you do things to increase PD, then you see PF also increases. You can see pictorially, right? PD plus PM is how much? PD plus PM. Because look, this is PM, right? That's PM. The area under any density function is 1. So many ways you can conclude, right?
Do we have ways to separate the PD and the PF, make one increase and one decrease?
That's what I'm saying. From the diagram, it is clear to you it's impossible, right? Because look, both PD and PF are on the right side of two different graphs. So if I move the threshold to the left or right,
So
PD and PF will either increase or decrease together. I'm also going.
no matter what detection scales we use.
Remember, this is the optimum, right? I mean, if it is not Gaussian, you will have some other density function. So if it is not Gaussian, you will probably have something like this. One density function. I mean, one density function, let me call it FLH under H1, right? And then you have another density function, right? Let me call this FL under H0. Somewhere you are going to say, this is my eta, right? Then what? Then of course, this is going to be PD and the other one is PF. Both are, you can see, if I move this left, both are increasing. If I move to the right, both are decreasing. So this is only a heuristic explanation, but I will, either today or tomorrow, I'll prove it for you. So let's complete this question quickly. Anybody has class immediately? 10 minutes are okay, right? Because your next class is at 6, I think, right? So we'll stop around 5:40 or as soon as this is done. So you see, you know the density function. Of course, this is 1 over square root of 2 pi sigma squared over n e raised to minus L minus a over squared over 2 sigma squared over n. Similarly, this is 1 over square root of 2 pi sigma squared over n e raised to minus. So let me plug this in here to find out PD and PF. So this is gamma to infinity 1 over square root of 2 pi sigma squared over n e raised to minus. Now you see no r, L, everything is in L minus a the whole squared over 2 sigma squared over n, right? And similarly, this one is a gamma to infinity 1 over square root of 2 pi sigma squared over n e raised to minus L squared over 2 sigma squared over n t L, right? So let's make a simplification. Here I'm going to put L squared over sigma squared over n. We'll start with this equal to x squared, in fact. So I'm going to take the square root of this. So this reads now e raised to minus x squared by 2 in the numerator, right? So you see dl is dx multiplied by the square root of sigma squared over n. Square root of sigma squared over n will cancel. So here you have, so this is the normalized Gaussian, you see, that's what I want to bring it to. Because with the zero mean, unit variance, so this is dx. Anybody, what happens to the limits? The top limit is infinity, so that stays the same. What happens to the bottom limit? When L is gamma, you plug this in. So that's square root of n gamma over sigma, right? The lower limit. Now, let me call this quantity to be something. Let's say a quantity C, okay? So this is the integral from C to infinity. That's what this is. This is, what is it, PD? Or what am I doing now? Oh yeah, we are looking at PF, right? So this is PF, right? Now remember, this is a Gaussian curve. You know this curve. This curve is 1 over square root of 2 pi e raised to minus x squared by 2. This is from probability, this area is tabulated. You can look up a table. That's the advantage. So this is called a normalized Gaussian, right? With the zero mean and unit variance. So then it is somewhere to infinity. Somewhere to infinity. From 0 to infinity, how much is it? Half, right? And so from 0 to 3 is already, from minus 3 to 3 is already 0.99, right? So 0 to 3 is already 0.499, etc. So from whatever. Then you can, so this area is known as error function complementary of C. So it's an error function, okay. So bottom line is our expression is error function of our C. Instead of C, I'm going to substitute the square root of n gamma over sigma, okay. So now let me plug in gamma here. This is gamma, right? So gamma is a by 2 plus sigma squared over na log eta. So I should multiply, C is what? C is square root of n gamma over sigma. So that's going to be A over, I'll tell you why I want to do it this way. Right? A 2 sigma, I put the square root of n here. Then sigma cancels, square root of n cancels. So I have again sigma over square root of n over A log 8, right? Now look at here. Anybody knows what this quantity is? It should be physically meaningful. This A is the signal power, A squared is the signal power. This is the output noise power, right? Sigma squared over n is the output noise power. So if you want, you can call this SNR output. So square root of SNR is A over sigma over n. So if you look at this, this is square root of SNR. This is 1 over square root of SNR. So my point is, you see, you can write this as square root of SNR over 2. You don't have to, but this is some, and log eta over square root of SNR. That's the, so you get, it's a standard expression. We just showed that probability of false alarm in this case is error function complementary log eta. Of course, if eta is 1, the first term is gone. The square root of SNR plus square root of SNR by 2. Let me quickly find out PD also, then we can quit. Yes? No, I know. This is fine with you, right? All right, so let me use another color. So it's almost here. Let me put this to be L minus A over sigma over square root of n to be y. So this integral is going to look like So you see dl will be what? Y multiplied by sigma over square root of n. Sigma over square root of n will cancel. So you get 1 over square root of 2 pi e raised to minus y squared by 2 dy. The only thing is in the limit. So when you put gamma here, you have gamma minus a over sigma over square root of n. So this to infinity. So the answer is error function complementary, that new constant, gamma minus a over sigma over square root of n. So I'll do that quickly here. It's already here. So if you, what is gamma? Gamma is here. So what is gamma minus a? Remember, you have a by 2. So this becomes minus a by 2 plus sigma squared over na log eta. Then if you multiply by square root of n, you will get exactly the same expression with the minus here, right? So you should be able to see that this is the same as error function complementary. The first term is, remember, it's exactly the same way. You multiply by square root of n over sigma. You multiply here also square root of n over sigma. You look at here, what is the difference? You have, here you have minus, here you have plus, exactly the same expression. So you will end up with this expression with a minus sign here, which is what I'm going to copy there. So it will be exactly the same as, so this will be log eta over square root of SNR minus square root of SNR by 2. So that's the PD. So let's see whether it makes any sense here. So I'll copy that result, red result here. This integral we already saw comes out to be error function complementary log eta over square root of SNR plus square root of SNR by 2. So which quantity is larger? So let's see. Remember, error function is, everything is based on one density function. Which density function is this? The normalized density function, okay? Look at this number, some number plus something. So this number is log eta over square root of SNR is here. Then you are adding something, so this is going to be log eta over square root of SNR plus square root of SNR by 2. In other words, you push square root of SNR by 2 this way, and then you look at this area. That's going to be PF. Look at PD. From here, from the same number, you go back. So you go back square root of SNR by 2. And then you look at this area. So physically you can see that PD is greater than PF in this case. So this is PD. But you see, I already showed you earlier, if you change the threshold, both increases. That let me show you next time. And so this is what I mean by solving a problem completely. So what happens if you increase the SNR? Look here, if you increase the SNR, you can physically see this. If you increase the SNR, this line, because this goes to infinity, this goes to 0, right? So this line goes towards 0 is here. So this line goes here. And if you increase SNR, of course, this line gets pushed to the right. So PF decreases, and it looks like PD, this line goes left. PD is increasing, which is what you want. So if you want to increase the SNR, I mean, you want to increase the probability of detection, then you need to increase the signal to noise ratio. Just by changing the threshold alone is not going to do it, but changing signal to noise ratio is more energy, more work, right? So if you, I guess it was you who asked how to increase PD and decrease PF. All right, so you see the answer here. If you want to increase PD and decrease PF, you have to pump in energy, signal to noise ratio. That means signal to noise ratio is what? A squared over sigma. I mean, what I meant was, let's say output signal to noise ratio, because it is sigma squared over n. So we can call it output. Without the n, you can call it the input signal to noise ratio if you want, right? Input signal power divided by noise power. So I should have, yeah, I put it here. I should have put a 0 here. So everywhere there is a 0. Okay. Output not 0 O for output. So if you increase the signal value or decrease the noise, one of them you have to do, then SNR will go up, or you can increase n, right? The number of observations, also good. That's under your control, because then the output noise power will decrease, overall signal to noise. So there are three ways to increase PD and decrease PF. You can increase the A amplitude, decrease the noise power, which may not be in your control, but you can certainly take more samples if both fails, right? So you couldn't have made all these deductions without actually solving the expression. That's what but you can't just look at it and decide. So look here, if n increases, even if n increases, PD will increase and PF will decrease, right? Because if n is increasing, SN signal to noise ratio is increasing. That means this number is going to the left. And this is going to the left of that. And then you have to work out and see, of course, this number is going, this is going left, but then this is increasing. But you have to see which one is decreasing faster. And so the question is, actually you'll have to work it out and see whether indeed the signal, whether what is the relation between the PF, the exact relation between PF, PD is given by this. What I will do next time is actually derive a relation between the two, PD and PF. Let me see how much time we have. So any questions? I think we are sort of running out of time. So let me ask you to, at least those of you who did, see whether you can do this, and I'll give you an outline. Remember, we have already expression for PD. PD is gamma to infinity probability density function of L under H1 dl. PF is probability gamma to infinity density, the sufficient statistics under H0 dl. My question to you is, can you use the, I want to find out, I think some of you can do this, find out dPD by, I want to find out dPD by dPF. So I'll give you a clue. So you can write this as dPd by d gamma and dPf by d gamma, but unfortunately you need to figure out how to take the derivative of this. Is certainly a function of gamma, right? Look at here. Certainly everything is a function of, this is gamma, right? So why don't I leave this, maybe you can take this as the last homework problem. Let me give you, I think some of you may be familiar. Let me give you this integral, a formula that will help you. Maybe you have seen this. So our case is a special case. I want to take the derivative of h with respect to x. So the formula is, you can see this in any book, derivative of b, the top limit, and then substitute wherever the variable of integration is the top limit, minus the derivative of the bottom limit with respect to x, of course, substitute the bottom limit. And the third term is the limits stay as ax and bx, and the inside you take the derivative. So it's not enough. The derivative of this is not just the derivative of this. Of course, if these are constants, these terms are absent, then this is right. So why don't you use this formula to derive this and see what is the third homework? I want you to show that this is positive if you can. What is positive? PD by PF. So you will see that PD PF always has this relation. It takes a little more doing because you also have to show the second derivative. But at least to see whether you can show that dPd by dPf is always positive. So the slope is always positive. So it cannot go like this. Then the slope will be negative. Tan theta, right? Theta need to be less than 90 degrees. So that's a general, nothing to do with this specific problem. Always dPd by, you can, book as a complicated argument, but you can use this and derive a neat expression. If you can do this, see whether you can do the second derivative and show that the second derivative is negative actually. D squared PD by dPf squared is negative. See whether you can show these two. This will be problem number 3. If not, I'll do this in class for you and I'll bring you the solutions for the other ones. Again, one more time, any questions? Yeah, ask me.
Why do you say this one?
Why do you use L because that's the average inverse?
Why square root of n? Why 1 over n?
What's the use of it?
Remember, that's the decision rule. In other words, look at what we are saying. You have given data R1, R2, etc., Rn. What do you do with it? You have to make a receiver. So the receiver action is, we just proved that sigma Ri is the right thing to do. Because when you simplified, the likelihood function came out to be this, right? Listen to me. We collected the data, we went through all this, we found the two density functions, right? And in this problem, it simplified to this. I mean, this is a constant, it doesn't matter. But then now this needs to be compared with some threshold. So this, remember, you have measured the data. So if this data exceeds the threshold, you say there is a signal present. So if the data is less than the threshold, then a signal is absent. So your question is, why compute this? Without this, what will you do? You need to have something, you need to do something to the data to decide whether yes or no, signal is present or not. Of course, you can say, why don't I square the data and so on. So in this problem, this is not the right thing to do. The right thing to do is this, because we proved it optimally. So this is the receiver you are looking for. Remember, you are looking for to do some optimal processing. Maybe, so in this problem, the optimal processing is very simple. You just take the average of the data and compare it with the threshold. But you say, look, this is too simple, let me do something more complicated. No need to do that. In this problem, even if you do more complicated, you are only going to do worse than this, because this is the best procedure according to the Bayes criterion. You seem to be still confused. So let me suggest this. Go home and read it. And another thing is, you can also, not in exam, but after the class, you can certainly discuss with other people. Or you discuss it, you come over to my office, we can. So your question was scary to me. So you said, why did I do this, right? So the reason I did this is, look at the steps. You need to find out the likelihood ratio test in this problem, right? So I went through all the steps. And ultimately, I got the simple function. That you can see, right? At least I didn't make any mathematical error, right? So this is the best thing you need to do. There is nothing more, nothing less. Maybe you are disappointed because this is too simple function. Is that so? Don't worry, you will find more complicated functions as we go along. I don't know whether I answered you or sort of. What was the question again?
I mean, what's the use of the
Yeah, use is, as I said, the use is, we just found the test. So remember, the goal was to find the likelihood ratio test. Likelihood ratio test is take the average and compare it with the threshold. This is the test. That's the goal of this class. Given a problem, find the likelihood ratio test. For the problem I gave you, this is the test. For the problem that you have in homework, this will not be the test. Something else will turn out to be the test. It's your job to find out what it is. So where is this problem coming in? As I said, if this is all, the data you have is today's temperature plus noise, or somebody is saying, look, I measured it, maybe I didn't measure the temperature. So I have some observations. So is this some random noise or is it temperature plus noise? So the point is you add up the data and compare it with if you happen to know what you are looking for, and the threshold again. So a lot of questions, you could say, look at here, this may be unknown. My threshold also depends on A. So this is something we will address next week, how to stay away from all these subjective thresholds. And in radar, it's a big topic called constant false alarm, C4, constant false alarm techniques. And maybe you have heard about Neiman-Pearson test. If you haven't heard it, just do a little bit reading before you come. And you still something bothers you, come over, talk to him, or then talk to me. Right? So I'll see you next week. I will be here in the office next Wednesday, definitely, so you can also come and see me. Thank you.